Okay, hello everyone here. Thank you for joining us today. My name is Manuel Di Cerbo. This is my partner in project, Andreas Rudolph, and we are taking you today to a small journey about our open source project, the OsciPrime oscilloscope. And in this talk we would like to tell you about the project itself, about how everything came together, what it is about, and we want to give you as listeners here some tips that you could apply if you wanted to do an open source hardware and software project. And also we would like to refer you to the project. If you want to find more information, you can go to our website, OsciPrime.com, and download all the documentation about the project. So we took a lot of time to give you detailed documentation about the project, as well as the source code for everything, also hardware schematics, and so on. First of all, we want to start with the beginning of the project. It was here in Switzerland as a semester project at the Technical University Northwestern Switzerland in Windisch, and we had a bachelor thesis there. And before the bachelor thesis, where we made the first oscilloscope, we had a semester project where we would start with Android and an embedded platform to create a spectrum analyzer under the project name Using Android in Industrial Automation. And the goal for us there was to find out how you could use Android on an embedded system for applications in industrial automation. So the project is both. It is software as well as hardware, and everything in between, like firmware and CPLD code. Everything is open source, so you can check out the source code at OsciPrime.com. So first of all, the semester project was in 2009. Android was not really out yet. However, there was an embedded platform, the BeagleBoard. There were other embedded platforms as well, hardware platforms, where you could run an Android build and use it with a mouse and the usual screen. And what we learned there in the project was how to build Android, how to configure, how to compile the kernel, how to get everything together and boot it with U-boot, and so on and so on. And also how to use NFS file system, and all the technical stuff you would require to develop on embedded systems. And it was the initiation of our blog, android.serverbox.ch, where we release always our new findings. Today we are doing a lot with the Arduino, for instance. And it started there. Especially one blog post was pretty popular. It was porting libUSB for Android in 5 steps. So, what did we have there? The project looked like this. We had, on the bottom right, you see the BeagleBoard, which is our hardware platform. We have an OMAP controller there, and we have the Android source, or an Android build running on top of there. Then on the bottom left, on the top left side, you see a picture of our data acquisition front end. So this is a dev board for USB programming with a Cypress FX2 microcontroller, where we learn to program USB. And we attached via I2C interface a very simple AD converter. And with all that together, on the lower left side, you see a picture of our first Android application. It was a spectrum analyzer. So what we did is we gathered data from a hardware front end and processed the data on the BeagleBoard and then show the process data to the user. It is very simple. However, it involves everything from bottom to top, from hardware to software, up to user interface and OpenGL as well. Okay, so with that started, we had our bachelor thesis where we got a new project. And it was again under the name Using Android in Industrial Automation. However, this time we were required to create a an oscilloscope application that would sample at a much higher frequency, much more high speed, and process the data. And what we used was for continuous transfers, 6 megasamples per second with 2 channels on the oscilloscope, and that is not at the limit of USB, however, it ensures that you won't lose samples. And when you see here 6 megasamples for an oscilloscope, that might be pretty low if you compare it with purchasable big oscilloscope, like you find them in the market. However, keep in mind this is transient, so you can record the data, and it is not like only snippets of the data. So that was really, really cool. You could use it as a logger. And what we did, different than the first time, we created a hardware front end from scratch. So we had the Android application, the system setup of the embedded platform, as well as an added hardware on top of it. So it was quite challenging. However, we managed to get it together somehow, and we were quite happy that everything was running so far. And in the picture here you see the OsciOne data acquisition desk, if you will. It looked a bit like this. So you have a screen, a mouse, and keyboard. However, it's an Android application running there. And you see also the green stuff there in the middle. That is our hardware, which we created from scratch and which we used to collect data. In this case, from a function generator. And we are going to utilize that same function generator here too after in a 5 minutes. Okay, this was about the project, and we founded a company during our studies, Nexus Computing Switzerland. And when we finished with our bachelor thesis, we said, hey, you know, let's try this. Let's go completely Android, since we gathered quite some knowledge with embedded systems and Android. And we had a really cool technical blog where many people will go there, and we wanted to offer our services to customers who are trying to achieve something with Android. And in the future, we plan to still deliver those services. However, our goal is to somehow try this open source adventure and to create this open source hardware and be able to make a living of it and dedicate our knowledge and our expertise to the future of the project. And if you want to find out a bit more about our startup, then you can go ahead and visit nexuscomputing.ch, and you will see some more information about this. Okay, now, enough talked about the history before. Let's talk a bit about oscilloscopes. So, I don't know if everybody from you knows what an oscilloscope is. Here in the picture is a typical oscilloscope. It is pretty bulky, a heavy device. You have a screen and you can measure voltage signals. And the thing with the oscilloscope is that differs from a power meter or something like that, is you can actually inspect a voltage signal over a certain amount of time. Okay, so our goal was to create something like this, however, in a bit different form factor. As you can see in the picture, we would have, for the OsciOne project, which was the bachelor thesis, a hardware front end, which you can see on the top, where we have AD converters, some low-level logic, a CPLD, a USB controller, and then we would take this data and ship it over to an Android application, which we would run at that time on the Beagle board. And then the user interface would have was a screen with a mouse and a keyboard. So pretty classic. You could take a computer for that. However, it is much more low power and much more fit for industrial purpose if you have an embedded system. Okay, and then OsciPrime is the project that we created after that bachelor thesis. And you see, one thing changed here, it is the user interface and the device. Since ahead of time there, well, during the bachelor thesis, there were no tablets. However, it was always in our mind that we could somehow use USB on a mobile phone at that time, or a smartphone, and to hook up somehow those. And that became suddenly possible in 2011, when we even had an announcement from Google that they created a USB host API. So you could suddenly use our scope with a tablet that featured USB host. And so we revamped the software completely in 2011, and then there was another revamp of the software in March in 2012, and we were about in June finished with the software and released it on the market, and ever since we got quite a good response for it. And we would like to talk about this new project. Okay, Andreas is now going to talk a bit more about the hardware, since he's the expert on that, and afterwards we are going to look a bit more into the software.
Thank you, Manuel. Hello everybody. I would like to welcome all of you to the presentation of our project. And in the next few slides, we are going to have a close look to the custom front end that we built. So that's the upper part of this slide. And what is really the purpose of this custom front end? As you can see to the left, we have analog voltage signals, and the output of the custom front end is digital data that is transferred over USB. So the real function or the purpose of the front end is that we have that we need to tap voltage signals, and these voltage signals, they need to somehow be adapted for the AD converters, the analog to digital converters. And as soon as they are fed into the analog to digital converters, we have digital data, and this is fed to the USB controller, which in turn will ship this data to the Android device. So when creating such a hardware, this requires a lot of simulation and also layouting and stuff like that. We're doing the schematics. We just want to give you here a quick overview of the hardware front end. Don't worry, we are not going to discuss this in detail. As you can see on the left side, we have again the probe inputs for the analog signals. Then in the middle we have the AD converters, the ADCs, and to the right we have the USB connector. We're going to have a slightly simplified version on this slide. And as you can see, again, we have on the left side the signal source. Then these signals are adapted to what we like to call the analog front end. In the middle we have the AD converters. And to the right, there is the digital front end. As you can see, there's an FX2 microcontroller for USB, and there's also a CPLD. CPLD is the master for the FIFO queue that the FX2 uses. So this slide is somehow outdated. We have a continuous mode where we sample at 6 megasamples. And we continuously transfer all data over USB. In the current firmware state, we have some other modes where you can use single channel only, but then you can measure up to, you can sample up to 24 megahertz. So it's 24 megabytes continuously transferred. So that's that for the custom front end. Now Manuel will give you a closer look to the Android software.
Thank you, Andreas. Yes, I would like to talk about software with you. However, I think it's well, the best idea to make that, to visualize that with some live demo. However, I want to just give you one example of the software architecture of the Android application, so you have an idea of what is going on in the software, and if you want to have a look in the source code, it gets you a quick start. So what happens here is we have a user interface where we have multi-touch and everything, and we display the data samples, and that's the upper part of the graphic. We have the user interface, and behind the user interface, when you sample data, you have a continuous circle or cycle where you where you gather new samples via USB and then display them. And this is, well, probably the largest challenge, how to ensure that you do not lose samples, and we achieve that using Java native interface as well as a buffering system where we buffer data on USB. And what we do is we issue new USB in transfers to our endpoint on the device, and those transfers get back with the data, with the left and right channel data. Both are 8-bit, and we are processing that data to be displayed to the user correctly, and we are doing some triggering, some interleaving, some scaling, and so on. Everything in native C code, since the performance of Java is just not enough for it. So what we have is this continuous cycle where we acquire data, we process it, and then again request new data, and the data gets displayed to the user. And this is probably the most challenging aspect of the software. Okay, at this point we would like to give you some live demo. I installed here a webcam which will show the tablet screen. We have a Nexus 7 device here, which features USB host with a USB on-the-go converter. And I will go and switch to the screen over here. Okay. So what you see here is the oscilloscope application. You can do cool stuff with it. You can pinch zoom, you can reset the view, you can shift around the voltage signals. Of course, you can change background, grid color, and so on. So let's go here. Green. And what we're getting here is audio data. So not only do we support USB, but also audio data. And you can download actually the application from our website for free, or you can go to the Android market and support our project by paying 5 Swiss francs for the project and download the application. However, both versions are completely identical, and you can also download the source and play around. So what we do now is we hook this oscilloscope up to our real hardware over here. I want to show you a picture here. My cam froze. This is well, now it should happen. Okay, just bear with me for a second. I will restart the application. I hope it will run. I want to show you the current version of the oscilloscope. We were in development phase for now about 6 months, and we have actually the first. Yes, of course. We have the first batch of hardware devices available now for pre-ordering, and we plan to ship in November. We have here some preview material. And we also have the prototype here, which we created during the bachelor thesis, and you can see the difference of the hardware design and the layout. So we are back. Okay, so this is the hardware. You have a USB connector over here. You have the BNC connectors here and here. And you hook up a normal probe like this to the oscilloscope. Okay, and this here over here is our prototype. And you see we made quite some changes. The new layout is a lot smaller. It is also a 4-layer print. The prototype was a 2-layer print, and the prototype also had components on the back, which the new doesn't. Okay, enough with the photos, and I'm going to slightly adjust here the camera. Okay. So we get this running. what I'm doing now is I'm hooking up the micro USB cable here to our hardware. And I will stop here the audio source and select the USB source. So what you will be now requested or prompted for permission, and you will get prompted again since we are uploading the firmware every single time into the device's RAM. So what happens is the USB device is re-enumerated. That is why you actually get 2 times ask for permission. Okay, and we already have a signal running there, which is pretty low frequency probably. And to see a bit more of the signal, you can go to the settings here, and you can say how many points you want to display on here on the screen, and then you can introduce some interleave, and what you see here is the output of our function generator. So, to fine-tune it. Maybe we can see a rep signal. Much more fun. Okay, so what you have is a trigger. You trigger the signal. Of course, you can zoom in. You can take a screenshot and export it and send it to your best friend. Show them what cool signal you just measured. You have measurement handles. We try to, you can see here, we try to use the touchscreen as, how it is supposed to be used with an oscilloscope. You get, for instance, the frequency displayed on the bottom here. You see the frequency is about 2 kilohertz. Then you have options for the trigger. You can either trigger on channel 1 or channel 2, or on a falling edge, for instance. And well, it's pretty much what you would expect from a normal oscilloscope. We have also some news here, which you can display and give you information about the latest things. You can go to the website. Okay, we do not have internet here. And also you have different, and this is done in hardware, you have different amplification levels, so you can measure different voltage signals, and at the moment you can measure from plus minus 1.8 volts to up to 16 volts, plus minus 60 volts. Yeah, so there were our efforts here for the software as well for the hardware during the past few months. And I'm going to unplug this since it drains a lot of battery. And we would like to present you, here it says Outlook, we would like to present you how you will get started or can get started pretty cheap with prototyping your own hardware before you go into production, and what makes sense and what will affect you. And Andreas is going to tell you how this works.
So as you can see here in this picture, this is was our assembly station, and usually you would think that all this costs quite a lot of money, but everything that we have here altogether costs maybe something around 300 euro. So what we used was the technique reflow soldering, and this is the like on the right side you have this box that you use for heating up the PCB, and then the solder will get the fluid and it will stick pretty good. So what you need for that is of course a bare PCB. For instance, you can do this at PCBpool.com or Beta Layout, I think it's called. And if you do just one, it will be maybe 60 euro. But if you want to make 3 or 4, prices go down. So that's pretty good. And what you also get at the PCB pool is a free stencil. So the stencil, as you can see, is a small plate, and it has openings where the footprints of the components will be. And what you do then is you need to fix your PCB, and you put the stencil on top of it, and now you can see that the openings, this is the place where the solder has to go afterwards. So you need some kind of palette knife, and you will apply the soldering paste, and then you can put your components on there. Of course, you have to be somehow careful, because some of these components have up to 100 pins, and yeah, you need to have a few tries, but usually if you place it in the oven afterwards, it will suck to the right direction, and yeah, the outcome is pretty good most of the time. So as you said, you put it in the oven for around 3 minutes, and then if you do this around 6 times, then you get 6 prototypes. And what we also want to tell you is, of course, you will need a soldering iron, especially if you need to repair some stuff. Maybe some components is broken because you touched it in and you were electrically charged or something like that. So also soldering iron can be pretty pricey. The one that we got here is costs only around 70 euro, and it even has a hot iron air gun, and we use this for desoldering, especially if the components has, like you said, up to 100 pins. It's a pretty good technique to desolder the component. So that's that for the hardware assembly part. And also for this presentation, we would like to hear questions or have an open discussion.
How did you design hardware? Did you use some tool?
Yes, for the specialties we used Eagle. You can do your schematics and also the layouting part. And then you can just send this file to a manufacturer, and yes, they will do the PCB.
What's the latency from when the signal is first received on the board to actually being displayed on the screen?
They're instantly, well, they have there's the FX2 microcontroller is hooked up directly to the CPLD, and we sample about 400,000 samples. And we did this since it takes about 32 milliseconds. And with that, we get the rate of about 30 frames per second on the screen, so we have a fluid display. So the latency is one buffer, is about 400, it's about 32 milliseconds. But you can do this however you would like, since you only gather data. You can display, you can create your own libUSB software, which isn't that complicated, and then you can display smaller buffers or bigger buffers or anything, or you can even change the Android firmware. However, you need them to adjust the time scales.
And there's a question about the FFT. So, do you have? I mean, tablets are not known for their CPU power, but they're sufficient for.
We're not doing FFT in this project.
Okay.
However, we studied a lot about other ways of how to calculate on the BeagleBoard the FFT, and we also were dealing with the integrated DSP processor and the Neon instruction set, which has single instruction, multiple data. However, it is, it's pretty complicated and deep going. But good question, thank you. Yes, at the moment we do not have any logging. We got requests that people would like since it's quite unique that you have a data acquisition platform that samples that at that high frequency, we got requests that we could somehow implement a logger where you would log data over a few seconds, since on your device, on an Android tablet or whatever, you have a pretty large buffer or a pretty much RAM where you could, just put stuff into and then afterwards inspect what you collect. And we're definitely going to address that in the coming, in the upcoming time and our upcoming development.
Presumably, as it's a USB device, you could also plug it into a PC or...
Exactly.
Yeah.
We already have a version that we use where we created some tool. Since every single device you see here, it gets a serial number from us, and we pre-calibrate it. And we have an automated process where we wrote up some Java code with JNI and libUSB, where we hook up the scope on the computer and then collect data samples, and we output on the function generator a sine wave where we know exactly what amplitude it has, and we calculate the scaling factor, since every single hardware has a different scaling factor for each attenuation setting. And we do that already automated with libUSB on the Linux desktop. So our goal is that in long term we are going to have some sort of support for the Linux desktop, since the project is open source and everybody can hack into it. And I don't know if you ever heard about the SIGORG project. However, they were interested in what we were doing and they plan to support our hardware. You should definitely check them out. I think they're really good guys. Also, the price of the scope is 249 Swiss francs, excluding taxes. And you can order it on the website. So we have, as an announcement, we have 3 devices here. So if somebody is sitting in the room and saying, hey, I need to have this, then you can get in touch with us after the talk, and we would like to demonstrate you. One restriction though, you need to have a USB host capable tablet, and not every single USB host capable tablet supports the Android host API. There is one tablet it is from Samsung, the 10.1 inch tablet. It supports USB host with the on-the-go stuff for external storage, mice and input devices. However, it has a kernel whitelist of those devices, so you hook up our scope and it won't enumerate. And that is the sad case at the moment with many manufacturers. However, if you have a Nexus, a Galaxy Nexus or a Nexus 7, it will work. Or an Acer, they have Acer tablets with USB hosts, it works too. Yes?
How well are the inputs protected? Like if I give more than 16 volts, what happens?
I wouldn't encourage to do it, but we have also tested up to 30 volts, and you can even go higher, because the input impedance of the scope is 1 mega ohm, and the current that is flowing into the first op-amp stage, operational op-amp stage, is goes through half a mega ohm resistor. So even if you even if you would go for 100 volts, but I wouldn't do it. But even then, it shouldn't break.
We have a small note in the boxes we ship that says, "Don't do it." Only if you really know what you're doing.
Or you could, for instance, use another probe. I mean, we designed it for 10-to-1 probes. If you use a 100-to-1 probe or 1-to-100 probe, then you can measure higher signals, of course, as well. But also, it's untested from our side, and we wouldn't recommend it.
So again, we will stick around for a bit more time here. So if you have individual questions, you can Here, I think from the program, we do not have any other speakers in this room, so that will not be a problem either. And at this point, thank you very much for attending. We are really pleased for such a large audience here, as well as the opportunity to speak at this cool event. And thank you so much, and see you around.